Okay, Module 7, in which we look at some applications for the theory that we learned last week. And I'm going to show you how to use Maxima to solve these problems. So the first application is mixing problems. Here it's with 2 compartments. We can generalize this to n compartments. If we've got n compartments, then it's an n-dimensional model. So remember at the beginning of the semester, we had this problem where we had a tank of brine, and brine was coming in at a certain rate and it was leaving at a certain rate, and we set up a linear equation which we could then solve to figure out the amount of salt at any given time in the tank. Well, we can generalize this to n compartments and we get an n-dimensional problem, and it's going to be constant coefficient as long as the flow of liquid into each compartment equals the flow out. If the flows are different, then the coefficients are no longer constant. That's going to depend upon T, because one tank is eventually going to empty. But for each compartment, we get a first order equation, and we figure out its rate of change by the simple fact that the rate of change is going to be the rate in minus the rate out. So let's have a look at example 4.4.4, which is around page 166 of the text. I couldn't get the picture to copy correctly, so there's a description of how the flow is determined. And we see that in each tank, we have 3 gallons per minute coming in and 3 gallons per minute going out. Okay, so this turns out to be a homogeneous system. So for example, in tank A, we denote the amount of salt by X. And how is that changing? Well, we have 3 gallons per minute leaving from tank A to tank B. Okay, so it's a minus because it's leaving. The amount of salt in tank A is X. We divide that by 50 to get the salt per gallon, and we multiply by 3 because that's the rate. So we have minus 3x divided by 50. At the same time, a gallon per minute is coming from tank B. The amount of salt there is Y. We divide it by 40 to get the salt per gallon, and we add that. Meanwhile, for tank B, 3 gallons per minute is coming from tank A, and the amount of salt in each gallon is X divided by 50. And at the same time, 3 gallons per minute is leaving, right? Because 1 for tank A and 2 for the outside. So we get minus 3y divided by 40. Okay. And we have our initial conditions, x0 equals 5, y0 equals 1, and so we get that matrix equation right there. And the question for you is, well, what happens if the flow into tank A from the outside was actually brine of 0.1 pounds per gallon? How would those equations change, and do we still have a homogeneous equation? Okay, let's use Maxima to find the general solution to this problem. So first, I'm going to define a matrix, that matrix A, same one down here in the lower right. Then I'm going to compute the eigenpairs using the command eigenvectors. And then a command there, that %, comma, numa. That's to convert, if you don't do that in, it'll put things in square roots and fractions. That just makes it computed as decimals, so you can see what numbers are. Okay, and so that's the output there. So we see our matrix A, we see our eigenvalues there, square root 249 plus 27 divided by 400. Not very good to deal with. So you see the numa actually says, well, that's actually minus 0.10695. Okay, and then we see the eigenvectors as well. Again, that command NUMA turns it into, in different systems, it'll give you eigenvectors in different ways. Maxima will always have sort of like the first component being 1. If you look at the textbook, when it gives its solution, it gives eigenvalues of length 1. I think that's because they're using Maple. So it all depends what system. And so anyway, from that output down the bottom there, I've been able to write down the general solution, and I've sort of done things to 5 decimal places. Okay. How do we solve our initial value problem? Well, we've got to find out what the values of C1 and C2 are. So first I define a matrix B, and if you notice, that's actually the matrix of eigenvalues. That's because it's at t equals 0, right? At t equals 0, all those exponentials are 1, and so our matrix B then is just the matrix of eigenvectors. If we were at t equals 1, for example, then we'd have to multiply the first column by e to the minus 0.10695 and the second column by e to the minus 0.2805. It all depends what happens at t equals 0. I'm going to invert B, and then I'm going to, I've defined there our vector of initial values, and then C dot V, that's going to actually solve for C1 and C2. Because if you look back here at our equation there, we want that to equal the vector 5, 1, and so you can think of this as a matrix times that matrix, that vector C1, C2. I invert that matrix, so the vector C is now going to equal B inverse times that vector V. And there we go. There's B, there's C, there's V, and then the output there is actually, we can just read off our initial, our constant values for those initial conditions. And so if you change the initial conditions, then you still use the same matrix, and it'll give you the values. And so that's then our solution to our initial value problem. You might think, oh, I don't want to type out all these things. You don't type them out, you copy and paste. That's the nice thing about using a computer. You have these numbers given to you to 10, 12 decimal places or whatever. You just copy and paste them. So to print the solutions, I actually just copied and pasted those numbers. So I defined functions x1 and x2, and ignore that and c2, and then I use that plot 2D to plot the functions, and notice I could put in what the values of c1 and c2 are, again copied and paste, and oops, there we go. That's the graph of our functions. The blue one is function X, which is the amount of salt in tank A. We see it starts at 5, and we see a nice exponential decay there. And then the red is tank B, and we see it starts off at 1. It increases, right, to around 2 pounds of salt as the salt's coming in from tank A, but it too seems to decay away. And so our here we've got a second question for the module is, what is that limit as t goes to infinity? That should be very straightforward. But what happens if we're in this situation of question 1 where the brine coming into tank A is at 1 pound per gallon? What are going to be the limits then as t goes to infinity? Okay, and so that is this application, and I'll get on to the next application.